Hi, my name is Heather Kuruvilla, and I'm Senior Professor of Biology at Cedarville University. I chose to come to Cedarville because it gave me the freedom to teach about creation in the light of Scripture. Creation teaches us about who God is, who we are, and where we came from, but it also has a lot of implications for our everyday lives. In my field of cell biology, most of what is known has been discovered because of research into cancer. So today, I'd like to discuss some connections between creation, the curse, and cancer. As you know from the creation story, after God had finished creating everything in 6 days, he looked at what he had made and he said that it was good. One of the biological aspects of the good design that God made is the process of homeostasis. Homeostasis is actually a strange word. Homeo means same, and stasis also means same. So the word literally means same. What the process does is it allows organisms to maintain an internal environment. Homeostasis is actually an essential and defining characteristic of living things. Non-living things don't maintain homeostasis, but all living things, no matter how big or small they might be, do maintain homeostasis. What homeostasis allows for is regulation of certain parameters, and it is an active energy requiring process, even though most of the time you're unaware that you're actually maintaining homeostasis. In order to have homeostatic control, you need some minimum components to your system. You need a control center, you need receptors that can give input to the control center, and then you need effectors that can make the changes necessary in the organism. So you need to have a place where input is received and processed, and that would be in the control center, and then the control center will send a signal to your effector, and changes will be made as necessary. So let's look at one simple example of this in your body. Let's say you're cold. If you're cold, thermoreceptors will send signals to the hypothalamus, where the control center for thermoregulation is in your body. The hypothalamus will then send signals to your muscles and tell them to shiver. Once that shivering has commenced, you will continue to send your signals back to the hypothalamus until you've actually reached the set point required for homeostasis. In some cases, you might just go get another piece of clothing, but imagine an animal trying to do this. In the case of an animal, the only way they're going to maintain homeostasis is actually by either changing their environment, trying to move somewhere warmer, or by doing something like shivering. When we look at the body, we know that you maintain homeostasis at the whole organism level, so at the whole person level, but you also maintain homeostasis at the cell level. And actually, there's many examples of maintaining homeostasis at the cell level. Here are just a few of them. So one of them is that cells were made to reproduce as needed. So in your body, cells will reproduce to replace themselves if they are old or worn out. And also in a growing organism, you would actually do a lot of cell division in order for the organism to grow. The cells have to reproduce at certain stages in the cell cycle. And there are things called checkpoints that God built to determine when it is safe for a cell to divide, and certain parameters are followed in order to determine that this happens at the appropriate time. One of the biggest aspects of cell cycle control is repair of errors. So our genetic code constantly receives all kinds of potentially damaging agents, whether that's from radiation, it can be from your environment, your own metabolism, all kinds of things can wreak havoc on the genetic code. Because of this, God had to build a system of repair apparatus called our DNA repair mechanisms. And those are constantly on guard, making sure that errors in the genetic code get repaired. If we have this functioning, it should protect us from mutations, and it should only allow cells to divide once they're properly repaired. In addition to all of this, cells need to relay and receive signals correctly. If you knew how many signals your cells were constantly receiving and relaying to other cells, it would blow your mind. Scientists still don't have a good handle on all of the reception that we're doing and all of the ways that that information is conveyed and relayed in order to maintain homeostasis. So reception and relaying of signals correctly is a large part of maintaining homeostasis at the organism level as well as at the cell level. One of the reasons that we have so many signals is for gene regulation. If gene regulation is not a term that's familiar to you, I'll define it for you just a little bit. So your genes are basically the information in each cell. Regulation of genes is basically turning them on or off as needed. And on-off switches in the cell are not like a light switch where it's a simple on-off switch. It's more like a dimmer switch. So you can turn a gene all the way off. That's the thing. But when you turn them on, you usually turn it up and down. So it's important for cells not only to be able to turn their signals on and off, but also to regulate them, to turn them down or to turn them up in response to all of the signals being processed from the environment. And finally, another homeostatic characteristic of cells is that in order to form organs and tissues, cells have to stay within their designated boundaries. If you have a liver cell, it should stay in the liver. You do not want that little dude running up to your brain. You don't want it going and binding to your spinal cord. You don't even want it migrating over to the lungs, kidneys, even something that's close by like the gallbladder. Liver cells are liver cells. They're supposed to stay in the liver, function in the liver, and stay within their designated boundaries in order to have proper function. If all of this is working like it should, you can see God's perfect design in creation. And so this cellular homeostasis does reflect the truth of Scripture that God pronounced about all of creation when he said that it was good. Now, remember when Adam and Eve hadn't sinned, there was no death. If all of these mechanisms were working perfectly in your body, you would have really good homeostasis, unimaginably good homeostasis. You would have no lasting DNA damage, so any damage that occurred to DNA would be repaired. You would have no disease. And in particular, when we look at cancer, cancer wouldn't exist because you would be repairing cells as fast as any damage could occur. You would have homeostasis at all levels of the organism, not just in the body, but even at every cell level. And if all of these things were perfect, then what God had said about his original creation would still be true. Everybody would be homeostatic, there would be peace, and there would be no physical death. When God made Adam and Eve, he created them special in his image. This has a lot of implications for how we treat people today and even how we see ourselves in relationship with God. God values us. He created humans special, and he gave Adam and Eve a special job that he didn't give to other creatures. He told Adam and Eve to have dominion over the earth, and he gave them stewardship of the Garden of Eden and of creation. He also told them that they could eat of any of the fruit that they wanted to, except for the tree of the knowledge of good and evil. Just this one single tree they couldn't eat from. And yet we know that they were tempted and they did eat of this tree. And when God discovered this, he cursed creation. A lot of what we live under today comes as a result of the curse that God pronounced on creation. It brought physical death and spiritual death to Adam and Eve. Now, the physical death didn't occur for a long time. However, the creation mechanisms of homeostasis that he had put in place were no longer perfect as a result of the curse. And this eventually resulted in physical death of those people. Creation as we know it today is subject to decay. And that started when God instituted the curse. Another thing that we see still today is that creation is no longer living in perfect harmony. Homeostasis isn't perfect. There's disease and there's death, but also even the relationship of organisms to one another is no longer perfect. And all of this has happened because of sin. There are definitely things that we see at the macroscopic and microscopic level that are all consequences of the curse. And this is by no means a comprehensive list of consequences, but it's a few examples. So let's start with the macroscopic ones, because these are ones you're more familiar with from probably church or Bible study. Things we know of like human nature being sinful. This happened as a result of Adam and Eve's sin. Ever since then, we are born into a sinful nature. And even though Christ can redeem us and break the power of sin, until we get our new bodies in heaven, we're always going to be subject to temptation and have these sinful human desires. We know that disease occurred as a result of sin and the curse because homeostasis is no longer perfect. Now we have errors, we have decay. These errors eventually lead to death. We also know that God pronounced that labor or work would be difficult. Now, God gave Adam and Eve work to do before the curse. So work itself is something God instituted that is part of the creation order and not a curse. However, after the curse, God said that labor would be difficult, and he particularly gives thorns and thistles as an example of things that Adam and Eve would have to contend with as they tried to raise crops and they tried to be able to live on the earth. In terms of consequences of the curse, most people have an easy time thinking of macroscopic examples, but the microscopic examples are often harder to think of off the top of your head. However, these microscopic examples have great implications for everyday life. For example, error-prone DNA repair is a consequence of the curse. What this means is that DNA repair is no longer perfect. Because of this, we are all accumulating mutations. These certainly contribute to aging, and they can also contribute to other diseases like cancer. Another microscopic consequence of the curse is faulty cell cycle checkpoints. Cell cycle checkpoints were built as part of creation being good. These checkpoints are God's way of making sure that cells only divide when they're supposed to and that they repair any errors prior to division. But now, because we sometimes have failure in these checkpoints, diseases like cancer can occur. Another effect of the curse that is seen at the microscopic level is non-disjunction. Non-disjunction is simply unequal partitioning of chromosomes, and it can lead to what we call aneuploidy. So let's use a human cell as an example. Most of the cells in your body are diploid cells. Diploid cells have 2 copies of each chromosome. However, an aneuploid cell would have either too many copies, like 3, or too few copies, like 1. For example, in Down syndrome, the affected individual has 3 copies of chromosome 21 instead of only 2 copies. In Turner syndrome, the affected individual has 1 copy of an X chromosome. In a normal cell, you would either have 2 copies of an X chromosome or an X and a Y in a male individual. Another microscopic effect of the curse is that signaling, which is what God provided to keep all of our systems in proper communication and properly functioning, signaling becomes faulty. This could be too much signal, too little signal, signals competing where they shouldn't. You can have defects in reception. You can have defects in all kinds of homeostatic processes, all as a result of faulty signaling. So I mentioned before that in cell biology, much of what we know about creation is because of research into cancer. Cancer is a really good example of how specific systems that God created to be good can become corrupted or broken one by one. And so what I'd like to do is give you a partial list of homeostatic control of the cell. And then for each of these homeostatic things that God created good, we're going to look at how these become dysfunctional in cancer. Like I mentioned, this is only a partial list, but I think that it gives you a really good illustration of the good in creation. So everything over on the left here is good. This is how God built things to work. And then everything over here on the right is dysfunctional and just represents effects of the curse. So let's go through some of these things. First here, DNA repair. I mentioned before that DNA repair is protective. It is there to ensure that we don't accumulate mutations. However, ever since the curse, DNA repair is present, but it's not perfect. In cancer cells, DNA repair generally becomes even less functional. And because of this, cancer cells have an increased mutation rate, which in turn leads to even more defects in the DNA. Another example of good creation that God made are tumor suppressors. So you have a whole bunch of genes that are known as tumor suppressor genes. These genes help control the cell cycle. They're called tumor suppressors because when they work, they keep cancer from happening. In cancer cells, tumor suppressors are often broken. When the tumor suppressors are broken, this leads to faulty cell cycle checkpoints. What this means is cells can divide, one, when they're not supposed to, and two, even when they do have defects in them. Normal cells have proper gene regulation. So genes are being turned off when they should be, on when they should be, and then regulated up or down in response to signals, just the way that God intended in order to bring about wellness for the cell and the organism. In cancer cells, gene regulation is often drastically reduced. So you have all kinds of dysregulation going on. We're going to look at a few specific examples of that. But if you summarize by just saying many genes that are supposed to be on are off, and genes that are supposed to be off are left on all the time, that's not a bad summary of what happens in cancer. There's so many things going on that it gets more specific than that, but you have a lot of gene dysregulation. One specific example of gene dysregulation is in the transformation or change of proto-oncogenes into oncogenes. So let's break those words down for a second. A proto-oncogene is a normal, happy, regulated growth gene. God built them with on and off switches so that cells would divide when they're supposed to, if the organism's growing, or if you just need new cells to replace old cells. But if these genes become broken or dysregulated, they are called oncogenes. Oncogenes are cancer-causing genes. They are dysregulated growth pathways that no longer respond to off switches. There can be a bunch of reasons that these happen, but in the end, what you get is dysregulated growth. You get growth either when there's no signal to grow, or you just don't have an off switch. So the cells receive the signal, they start growing, and they never turn off that signal. This would be very dangerous to the organism because the cells would just continue to divide, and eventually they would mess up the function of that organ. And if they spread around the body, they can potentially mess up the function of other organs as well. One characteristic of good homeostatic tissues and homeostatic cells is functional communication. This allows every part of the body to communicate with each other in order to maintain harmony. It also allows the cells in tissue to communicate with each other. Do we need to grow, divide, make proteins? What proteins do we need to make? Do we just need to sit here and chill for a while? What are we supposed to do? All of that communication happens on a millisecond by millisecond basis in the body. And without it, you have all kinds of disease. So when we look at cancer in particular, there is a lot of dysfunctional communication. Often, cancer cells are tone deaf. They are not actually hearing or responding to the signals that they would be receiving normally from their neighboring cells or from the rest of the body. So dysfunctional communication is a hallmark of the curse, as well as cancer in particular. In normal, happy, functional tissues, you have functional cell associations. Your liver is built out of a whole bunch of liver cells stuck together, talking to each other, doing stuff together. acting like a tissue. Your blood is formed of many cells that are not stuck together, but yet are still talking to one another. And so you have functional tissues and organs. This is how God made it to work perfectly and in homeostatic order. However, what you see in cancer are dysfunctional cell associations. We're going to look at a model of this, but if you've ever heard of the word metastasis in cancer, you probably know it's not a good word. What metastasis means is that the cancer cells are able to invade space that doesn't belong to them and spread to other places in the body. This is a result of dysfunctional cell associations. Normally, these cells would just be stuck to each other, doing their work. But if they are allowed to fall off their tissue of origin and potentially spread elsewhere, this is not the intended design in creation, and it is extremely dysfunctional and extremely harmful to the organism. Another thing we're going to look at in homeostasis is tissue remodeling. Now, tissue remodeling sounds potentially really scary. It sounds like you're basically going to take your kidneys and make them into a new shape or something like that. But all that is meant by tissue remodeling is that the body has the capability to break down broken or worn out components and rebuild them. So, for example, if you cut yourself, you would have a bunch of shredded cells as a result of cutting yourself. You'd have broken vasculature, you'd have shredded capillaries, you'd have a bunch of broken debris. And all of this needs to be cleaned up in order to rebuild the new parts that you need in your body, the new cells and the new tissue. So tissue remodeling under normal circumstances is a good thing. It allows for growth and it also allows for healing if you injure yourself. However, cancer co-opts all of these processes. And so we're going to look at two ways in which tissue remodeling can become a bad thing for the body. In the case of cancer, there are two ways in which tissue remodeling is co-opted for evil purposes. One of them is angiogenesis. The word angiogenesis means the creation of new blood vessels. This is normally a mechanism for healing. So like I mentioned, say you cut yourself, you would injure some blood vessels. In order to repair that damage, you would have to have angiogenesis. Angiogenesis would just allow you to replace the vessels that you hurt, and you'd also have some other cells come and literally eat up all the pieces of broken stuff. So you would have this as a normal part of healing. But in the case of cancer cells, what they do is they signal for angiogenesis, the formation of new blood vessels, in order to get themselves their own blood supply. They do this so that they can get nutrients and oxygen, and so the tumor can grow. So this is a bad thing for the organism. Another place where tissue remodeling comes into play in cancer is in metastasis. So normally, cells will adhere to one another and stay in their organ or tissue of origin. But in tissue remodeling, you do have breakdown of connective tissue that surrounds the organ. And normally we only do this in order to allow for cells to come in and allow for healing of the tissue. But in cancer, the connective tissue that surrounds the organ is broken down in order to allow cancer cells to escape. This is really bad because the cancer cells can then get into the bloodstream and use that basically as a conduit to get around the body, or they could potentially get into the lymphatic system, again, allowing them to get into other organs. So tissue remodeling is good. God created it for a good purpose, but it certainly can be co-opted and corrupted, and when corrupted, it can lead to things that very much detract from homeostasis. The last one we're going to look at here, by no means a comprehensive list, but still one that's really important for understanding cancer, is apoptosis. Now, apoptosis is kind of a strange word. It means programmed cell death. And believe it or not, programmed cell death is protective for organisms. So let's look at a couple examples of when this would occur. During development, when the body is forming the nervous system, for example, there are little spaces that have to be made between nerve cells. They're called synapses. So the way that you create a synapse is by having one single cell that used to be there commit programmed cell death, and then you have your little space. Or when you're forming fingers and toes in an organism, the way that happens is all of the skin and connective tissue that used to be between your fingers and between your toes actually committed apoptosis on a cell-by-cell basis. So all of those cells died in order to form a new structure, okay? In an adult, what apoptosis does is it allows you to kill cells that are so damaged that they represent a threat to the organism. So cells that might turn into cancer should actually signal for their own demise. If that happened, there would be no cancer, because anytime a cell got messed up enough to go that direction, it would actually kill itself and no longer represent a threat to the organism. One characteristic of cancer cells is that they often have impaired apoptosis signaling. So even if they're messed up and they know it, they can't die because their apoptosis signaling pathways have been destroyed. This model represents the progression from normal homeostatic tissue here all the way to cancer. This is not a comprehensive picture of what goes on, but you can still see some pretty major differences. So let's start over here with the normal tissue. You'll notice a few hallmarks of normal tissue. The cells are very orderly. They're arranged in rows. They talk to each other. They're stuck to each other, and they are all communicating with each other and carrying out a common function. So these are all characteristics of homeostasis. In hyperplasia, where we would not consider this full-fledged cancer, but maybe a step on the pathway toward cancer, hyperplasia is what it sounds like. So hyper usually means too much. Hyperplasia is too much division. Okay, so these cells are still relatively organized. There's a little bit less cell adhesion here. When you see that, that doesn't look good because it means the cells are not as anchored as they should be to one another, but yet this organ would still function pretty much the way it should. When you see this here where it says mild dysplasia, dysplasia means that you have some cells in locations where they shouldn't be. So we look at these cells and they are no longer as ordered as they should be. And this definitely impacts the function of this area of the organ. So in this area, you would have less function than you should just because the cells are not as organized as they should be. They're not anchored to each other as well as they should be. And they're even growing on top of each other in places where they should not be. So we'll move to this, and this is quite a jump up. They're actually in cancer progression. There would be several stages between these two, but you see here it says severe dysplasia. If you look at this compared to the normal cells, they look really different. Their shape is different. Their size is different. The way that they're anchored to each other is different. They are no longer nearly as organized. They are not anchored to each other as well. They're no longer communicating with each other as well. These cells are not doing the person any good. In fact, they're basically acting as a parasite. The only thing they're doing is draining your resources and impinging the normal homeostatic function of your organ. So this is not a good thing, okay? Everything that here was homeostatic and good is now corrupt. The only thing that these guys are not doing that they could potentially be doing that it would be worse is these haven't spread. Okay, so when it says carcinoma in situ, it just means that this tumor is still benign. It hasn't eaten through connective tissue, but it is acting as a parasite. It is not helping the organism at all. It is only harming it. All right, so if you move on to fully metastatic cancer, also called invasive cancer, it has acquired the ability to break down connective tissue. And that just means that now it can either recruit other cells to break down the connective tissue for it, or some of these cells may even express enzymes that allow them to burrow through connective tissue. In either of these cases, that would allow these cells to get into the bloodstream or into the lymphatics. And when they do that, they can travel around the body and find other places to go and lodge and grow. So now you have from here, where it was just a parasite in a single tissue, now these metastases will be parasitic on multiple tissues. And the more that this spreads, the more tissues become affected. And you can see basically everything that was good right here is corrupt here, and ultimately would take the life of the organism who was experiencing all of these defective processes. So let's go back and look at how the creation story impacts what we just talked about. So we know that in redemptive history, the story God tells us begins with creation. And we talked about how creation was when God pronounced everything good. He called things into existence. He hand created Adam and Eve, and he proclaimed and pronounced everything good. But since the fall of man, we have the curse. And ever since the curse has been pronounced on creation, creation is subject to decay. Or as Romans says, creation still groans. The effects of the curse are definitely still present, and we experience them every day. We know that Jesus came, and he came to redeem us. But Jesus has not yet come back to restore all things. And until Jesus comes back to restore all things, we still have the dominion mandate that God gave Adam and Eve. In other words, we still have work to do in order to take dominion over creation and to bring redemption. This is where science can come into play. So one of the things that science allows us to do is take dominion over creation. And depending on what branch of science you're talking about, it does this in different ways. This is definitely how cellular and molecular biology would work. So what I am teaching my students to do is basically this right here. First of all, in order to understand disease and to take dominion over that, we have to understand homeostasis. We actually have to go back to creation and see what is good about creation and understand how creation is supposed to work. If you understand how it's supposed to work, you can understand what's broken. So the next thing we do is unravel molecular causes of decay. What is causing the defects we see? What was that good design? And how can we get back to the good design? And so the last part would basically be trying to think God's thoughts after him in a sense, designing therapies that can restore homeostasis. Now, in some cases, you can really do a good job of restoring homeostasis. For example, if somebody breaks their arm and it's a clean break and a doctor comes and puts a cast on it, that's probably going to heal cleanly. And honestly, full function is usually restored in many of those cases. But in molecular biology, we're often not able to do that clean of a restoration. So even though we design therapies that are geared toward restoration of God's good design, sometimes we can only partly get back to homeostasis. And so I wanted to give you just a few examples of some of those therapies, and we will relate it to cancer because that's what we've been looking at. You can see some really good examples of how you can use science as a redemptive tool to bring hope as we take dominion over creation. So on the left, I have a bunch of effects of the curse listed. All of these effects of the curse are examples of contributors to cancer as a disease. On the right are a few of the therapies that are used against cancer. This is definitely not comprehensive. You notice I don't even have things like radiation or surgery on here, which are certainly important. And that's because mostly at this stage, I am looking at biochemical and molecular causes of cancer and looking at how would you actually deal with those. So what I tried to do is pair the effect of the curse on the left with a treatment that would act against that effect of the curse on the right. So let's just go through my list. On the left here, we mentioned before that one of the characteristics of cancer is that DNA repair doesn't work properly. And because of that, you have an increased mutation rate, and that often leads to an increased cell division rate. So one of the therapies against this particular effect of the curse are antimitotic drugs. Antimitotic drugs are what they sound like. anti being against, mitotic being against mitosis. So slowing down or preventing cell division. And if you remember what the cancer progression diagram looked like, you can see how that would make sense, because one of the hallmarks of cancer is cells are dividing when they shouldn't. So if you can stop them from dividing when they shouldn't, you can help treat that cancer. Another hallmark of cancer is having faulty cell cycle checkpoints. We mentioned that the tumor suppressors that God built as part of his good design are often disrupted or underexpressed or just plain broken in cancer. And so one of the ways that we can combat this brokenness is by using growth inhibitors, things that block growth, so that even though the tumor suppressors are not functioning as they should, we can stop the cells from growing when they shouldn't. Another hallmark of cancer is gene dysregulation. Now, this is an area of research that is just starting to bear some fruit in terms of medicine. So honestly, we'll probably get a lot more medications on this line of therapy as science continues to progress and we understand more of what homeostasis looks like. Gene regulation is incredibly complicated. Right now, one of the big needs in the field of gene regulation is mathematicians that study combinatorics. And if you know what combinatorics is, it's basically when you have huge numbers of possible combinations of things that can work together. Gene regulation is so complex that we only understand a tiny bit of it. And in order to truly understand what homeostasis looks like and understand the good design, we actually need to get a lot wiser in our study of gene regulation. However, even from the little bit we know, we do have some understanding of what genes are dysregulated, and we do even have some drugs that actually help push the cells back into the direction of homeostasis. So they actually promote gene regulation, whether that's turning on or turning off certain genes, which is really cool. Another effect of the curse we mentioned before were oncogenes. So we mentioned that proto-oncogenes are the good genes that God created that are regulated and promote growth of cells during growth of the organism or when they need to be replaced. But oncogenes are messed up proto-oncogenes, where you have dysregulated growth. The cells are growing when they're not supposed to. They haven't been told to, or maybe they are being told to, but they're not supposed to be told to. In any case, something is going on that should not happen. We know a lot of the pathways that are involved in growth. And because of this, we know how those pathways work, and we have a whole bunch of drugs in this particular category, which would be different signal pathway blockers. So if you know where a pathway is broken, you can try to block the rest of the pathway from happening, and ultimately you can cut down the rate of growth and keep that tumor from getting larger and potentially even help kill it. Another very strange characteristic of cancer that we're starting to understand better and better is that cancer cells can tell the immune system, basically, that there's nothing to see here. There is a local immune suppression that is done by cancer cells to the immune cells. So your immune cells do have the capability to fight off and kill cancer cells. However, most of the time what happens is the cancer cells will signal to the immune system, telling the immune system not to eat it, and that there's nothing wrong, and that the immune system should just chill. We don't want that, because what that does then is that allows the cancer to basically just pass undetected by your immune system. So what scientists have developed and are continuing to develop are basically overrides of this immune suppression, and those are known as immunotherapies. You may have heard of antibody therapies for cancer. Antibodies are proteins that basically are little flags to activate the immune system, and these have been very effective against some forms of cancer. More of these are being developed all the time. There are also even special genetically engineered cells that can fight cancer. These are known as CAR T cells, And if you want to Google them, you could find a lot of really cool information about them. But basically, if I had cancer, scientists could take some of my own T cells, which are immune fighting cells, basically. They're cells that would be able to kill the cancer cells. So they take T cytotoxic cells or killer T cells. They would engineer them to specifically recognize cancer cells. Then they would grow them up, so there's a bunch of them, put them back into me, and these cells would be like little soldiers that say, hey, cancer, you're lying. You're telling us that there's nothing to see here and that we should just chill. But we know better because we have been educated. And so they'll go in and they'll bind to the cancer cells, and they will give them basically the handshake of death and cause them to commit apoptosis, and those cancer cells will die. It takes about half an hour for a CAR T cell to kill an individual cancer cell, and it is a really cool process. The biggest downside of this therapy right now is the cost of it, but it is becoming less expensive, and it is also becoming more specific as scientists learn better how to regulate this treatment so we don't accidentally kill cells that we want to preserve. Another example of the curse that is seen in cancer are dysfunctional cell associations. In normal tissue, cells of a given organ associate with each other, but do not associate with other tissues. In cancer, we see two examples of dysfunctional cell associations. The first of these is in angiogenesis. Tumor cells will recruit endothelial cells. Endothelial cells then form new blood vessels. This provides an all-you-can-eat buffet for the tumor. The tumor then can grow and increase in size because it has all of the oxygen and nutrients it needs. If you want to restrict tumor growth, one way that you can do this is by blocking angiogenesis. Another dysfunctional cell association that occurs in cancer is metastasis. Metastasis is when cells can break off their tissue of origin, migrate through connective tissue, and then reach another organ and actually stick to it and start growing. This is dysfunctional on many levels. The cells were never supposed to break off. They're not supposed to eat through connective tissue, and they're not supposed to stick to other organs. So we have certain drugs called matrix metalloproteinase inhibitors, or MMPs. MMPs do not allow the cells to break through the connective tissue. This restricts the growth of the tumor to the organ where it originated and does not allow for metastasis. Finally, one effect of the curse that we see in cancer cells is that often they have defective apoptosis pathways. They have all kinds of DNA damage, all kinds of signaling damage, and yet they do not commit apoptosis and die. Usually, it's because apoptosis is somehow broken in that cell. Often, it's because of a broken apoptotic signaling. So there are a number of drugs that are given to help combat cancer that are actually apoptosis promoters. These drugs help the cell realize that it is damaged and needs to commit apoptosis in order for the organism to remain healthy. Now, sadly, none of these is a cure for cancer. All of these help treat the disease, but as long as we live in a sin-cursed world, we will continue to see all kinds of brokenness in creation. However, all of these things are examples of how science can be used as a redemptive tool to help restore homeostasis and help restore harmony to creation until Jesus comes back. Until the Lord comes back, we know we're going to have a lot of work to do. The dominion mandate is still our job. We are still called to be stewards, wise stewards, over all that God has made, and we're still called to bring harmony to creation. Science, biology, molecular biology is just one way in which we can do this. What I teach my students with regards to molecular biology helps them to become doctors who help heal. It helps them to become researchers who help understand homeostasis and ultimately design ways that we can help organisms achieve homeostasis even though the curse is still here. So if you're interested in this aspect of reversing the effects of the curse, I highly recommend checking out the biology program at Cedarville University. And until Jesus comes, may we all be good stewards of his creation. Thank you.